So we're talking about a comparison here. So I know 1 over x diverges, right, from the integral from 1 to infinity. Is everybody with me there? Right, I showed that, right, with the ln. We got the, okay, Serrano agrees. I can easily show that the area from 1 to infinity of 1 over x squared converges. So 0 is less than y, which is less than 1 over x squared. This one converges. Now notice that green area, and let me restrict it. Look at that green area. It's underneath the blue area, right? Do you see that? And so I'm kind of looking for that. If I know 1 over x diverges, right? And that's right where my limit is. If I get something that's underneath it, I have a good chance of converging there, right? That green area does converge. And so this is the essence of the comparison test, okay? Am I making sense at all to anyone? Oh, I hear our crickets or cicadas. I was in Gaithersburg the other day. I don't know why I was in Gaithersburg, but I was in Gaithersburg, and the cicadas there, it's like there's billions of them in the trees, and the noises, oh my God. I live in DC, and so everything is concrete. No cicadas. So I'm not making sense to anyone about this. Blue areas divergent, and that's that limit of where I'm going to get the, right? I said if 1 over x to the p, if p is bigger than 1, it converges. And so you see that green area is 1 over x squared. Let me write that. So this is 5.10 comparison theorem. Oops. So what did we say? We said of 1 over x to the p dx converges if p is greater than 1. Right? So the integral from 1 to infinity of 1 over x diverges. The integral from 1 to infinity of 1 over x squared converges. And I can use that 1 over x as kind of my breaking point for areas. Right? I can use that 1 over x piece. So that blue area is infinite. But almost all areas below it are going to converge. In this particular 1 over x squared, we could easily show converges, right? David, talk to me.
So you're saying let's see, the limit from 1 over x, the integral of 1 over x from 1 to infinity.
Yep.
That's like the smallest infinity, so anything that's less than that is infinity, is less than infinity, and therefore...
And finite, yes.
Finite.
Yes.
Because it's the smallest infinity, because there's bigger infinities, but it's smaller, and therefore...
Yep.
Right?
Yep.
Okay. And that's you're just using that as a benchmark.
It's the essence of what we're going to do when we do this comparison theorem. And so you got to wait for me, but I'm just trying to, I like a visual. I'm a geometry person, so I like to see what the hell is going on. And if you, right, the one we had just done before, right? The problem we had done before was what? X squared e to the minus x? Right? And so look at that purple curve. It's above the blue curve, right? Until a point, until this point right here, right there, the blue curve and the purple curve are the same. So from here to here, right? And can you see my mouse on the screen? From the area under the curve from here to here is finite. Any finite integral is finite, right? And so from here to here is also finite in terms of the blue area. But let's keep comparing the rest, right? After that, the blue area is infinite and the purple area is finite, right? We just showed it. Okay, let's jump right to a problem, and it's a little bit easier to see how we're going to do this comparison theorem. But we need something to compare to. That's the key. And so if we can compare to a 1 over x squared, right? So if we can compare to a 1 over x squared, which we know is finite, right? And by the way, you should do that. Show me that 1 over x squared is that area is finite. And then I look at 1 over x cubed. Oops. Since the green area is finite and the black area is smaller, the black area must converge, right? This is the comparison test. What I was doing before was just comparing something that was on the edge of converging to something that converged and we saw that it was lower, right? So, but the real comparison test is if we get something that's convergent and then we find something even smaller, if we find an area that's convergent and then find something even smaller, then obviously it's convergent. If we find something that's divergent and get some area that's bigger, obviously the comparison is also divergent, right? Is that making any more sense to anybody? Charlie says yes. David says yes. Angel says yes. Adam says yes. Nice. Charlene is there. Yes, great. Everyone else is asleep, or you have no idea what the hell I'm talking about, which is, I'm used to that.
When you say smaller, do you mean like smaller value and closer to the axis, like a smaller area?
Exactly.
Okay.
Exactly. All right, let's do a problem, and we'll see how you set up problems, and then you can try a couple. And once again, I'm in my office today till 1:30. You certainly can step away and come back. You know, I don't know if any of you are doing study groups yet, but it'd be a good idea to say, hey, anyone want to work on homework together today, or you know, and I know that's a lot easier face to face, but you can just compare problems together, email work back and forth, or show it to the screen. You know, you all have a Zoom account, so you certainly could create a Zoom to meet, right? So this is number 43 in the book. And this is we're doing this, we're going to say, is it convergent or divergent? Sorry. We're going to say convergent or divergent based on a comparison, right? So this is a 5.10, number 43. I want to look at the integral from 1 to infinity. Every now and then I accidentally closed my notebook, or it's just freezing. Now this one could be done with partial fractions and an improper integral, but it's nasty. It's a horrible problem. So it's nice to be able to do a comparison. All I care about, does it converge or diverge, right? So the trick is to look for the mother function. Now if you had me for Calc 1, you know I like to say mother function instead of parent function because it sounds like I'm cursing. Mother function. But the mother function is that leading term. So downstairs the mother function is x cubed, right? So I'm really comparing x over x cubed plus 1. I'm comparing that, right, less than equal, greater than equal to x over x cubed, right? So I'm chopping off those extra pieces. Now, I chopped off a positive number from the denominator. So what happened to my overall quotient? Did it get bigger or smaller? If I'm dividing by a smaller number, right? So let's think about it. If I had 50 divided by 10 compared to 50 divided by 5, right? 50 divided by 10 is 5, right? 50 divided by 5 is 10. So when I cut off something from a positive number from the denominator, I make my result bigger. Does that make sense? So I know that I'm talking about a less than symbol there, right? My original function is less than x over x cubed. And what is x over x cubed? It's 1 over x squared. And what happens to 1 over x squared? What happens to this integral? The integral from 1 to infinity of 1 over x squared dx. We didn't show it yet. You should show it. It's very simple. In fact, we can do that before we leave today if you want. But I know 1 over x to the p, right? That p series, they call it. If p is bigger than 1, it converges. So 1 over x squared, 1 over x to the 2.5, 1 over x to the pi, all of those converge. Any power bigger than 1 will converge. And very easy to show it. So this particular area is bigger than this area. And so since the bigger area is finite, converges, what's got to be true about the smaller area? Also converges. So you might be chopping off positive numbers from the denominator. You might be chopping off positive numbers from the numerator, positive terms from the numerator. You might be, et cetera, et cetera. You're just trying to break it down into mother functions and then could do a comparison and see which one's bigger, which one's smaller. And graphing helps, right? Graphing helps, that type of thing. Should we show that 1 over x squared converges? Do you want to show that?
I have a question.
Yes, Angel.
So, comparison theory, would that be like a question on our midterm?
I don't usually ask it on the midterm. I haven't in I think 4 or 5 semesters. And I think looking at the last 3 midterms, that's really what I'm shooting for this midterm. This is a good conceptual concept that will help us in Chapter 8. I mean, I usually will just go back to this section but I feel like this class is very strong, and I don't feel like I'm doing too much at this point. But you'll tell me, please. I'm talking to everyone. You'll tell me when you're overwhelmed. You'll tell me if you're having trouble, right? Otherwise, I think everything's fine because I'm stupid. Well, I'm a man, first of all, so pretty stupid. Unless you tell me something, I'm going to think everything's fine. So, but you got to get some work done, right? You got to get some work done. Yes. Is that Ash?
Yeah.
What's up?
Why did x over x cubed become 1 over x squared instead of 1 over 3x squared?
I didn't do derivatives, right? I did. I just reduced, right?
Oh, okay.
Right. So I had an x over x times x.
Right.
Right.
Yeah. Thank you.
Yep.
And so with this, like if x over x cubed plus 1 was larger than x over x cubed, it just wouldn't tell us anything, right?
Exactly. Yeah.
Okay.
Yeah. You. If one converges and the other diverges, you're out of luck. You can't. Right. You need both to converge or both to diverge. So in the convergent case, you need the other one to be under the area. Mm-hmm. And in the divergent case, you need the other area to be over.
Right.
Yep. Good question. So let's just show this one converges real quick, right? The integral from 1 to infinity of 1 over x squared dx. I know I need a limit, but I can also do the integral right away, right? So this is the limit as a goes to infinity of negative 1 over x evaluated at a and then 1. And of course, yes, I did that integral fast, but do the derivative for me and you'll agree, right? The derivative of 1 over x is 1 over x squared, right? So and the negatives will cancel. And so then evaluate this at a and evaluate it at 1. And then I need the limit, right? And of course that limit goes to 0. So in the case of when we're just saying, all right, is it convergent or divergent? I mean, I could do this one with partial fractions. It's hideous. It's hideous. It's 4 or 5 pages long. Okay, so, but I can do a comparison sometimes. And so what am I really saying to this about us in our field? I now have a model that works. So I can go ahead with the experiment. If I came up with this model and I showed it was divergent, it doesn't work. Can't. I got to do something else, right? And that's what we're trying to do in the real world with mathematics and bio and engineering. We're trying to come up with models that will predict what is going to happen, right? And so if our prediction machine is finite, that's good, right? Let's do another one here. So there's only 3 problems to do for comparison test, right? So maybe we'll do another one. I'll do number 44. Okay. I'm pretty sure there are no comparison test problems in WebAssign. So try 43, try 45. If you can do those, you're done. Right? It'll just help us later in chapter 8. Okay? I can't test you on everything. Thank God. It would take me forever to grade it. So compare, right? So what do you think? I mean, do you see something we can chop off that maybe is not making that much of a difference?
2.
I think the 2 also. My gut says the 2, right? Okay. You going down to the room? Okay. I might stop by at an office hour. I'm sorry, I was talking to my girlfriend. So I think the 2 is the way to go. I mean, I'm taking off a constant, right? I know e to the negative x is always positive, right? So I'm chopping off a chunk from the numerator, right? I'm chopping off a chunk from the numerator, right? So what happened to my end result? Did it get bigger or smaller? If I took $2 out of your pocket, did your amount of money go up or down?
Or
Smaller, right? So I'm thinking my original integral is bigger than this integral. Now, if this new integral converges, this doesn't tell me anything. But if it diverges, if this one diverges, then the other one has to diverge, right? So just because I do a comparison doesn't mean it's going to give me a definite result. And maybe I switch the comparison if it doesn't, right? But clearly there's a mother function already downstairs, right? And upstairs there's a function plus some constant. So I'm saying let's strip it down to the thing that's really controlling. And the thing that's really controlling the numerator is the function e to the minus x. So we want to know if this particular piece diverges or converges, right? So I want to look at the integral from 1 to infinity of e to the minus x over x dx. So this one, it doesn't necessarily look like one we've done before, but it looks like I would have to do it by parts, right? Now what's funny is the original integral I don't know how to do it. The original integral I don't know how to do. And so we actually have it wrong. So I like this idea. But I actually want to cut off the e to the minus x. So I got this new integral to do, and then I went, well, how do I do that? I got to do it by parts. And that's not the way this comparison thing should work. It should be obvious. Sometimes I guess, so I could have done this, and I could have done it by parts, and I would have shown divergent, and then I would have shown the original divergent. But look at this comparison now. Now, what did I cut off from the numerator now? What did I cut off from the numerator? A positive number or a negative number?
positive number.
It's a positive number, right? E to the minus x is always positive, right? If I think of that curve, e to the minus x, it's always above the x-axis. So I'm just cutting off positive numbers from the numerator. So again, the result got smaller. And what do I know about the integral from 1 to infinity of 2 times 1 over x dx? This is divergent by the p-series. So since 2 times the integral from 1 to infinity of 1 over x dx is smaller than the original 1 to infinity of 2 plus e to the minus x over x dx, we know that they're both divergent. So what do we see here? I go to do a comparison, I cut something off, it makes the problem difficult. I cut something else off, and it makes the problem easy. And that's what we're trying to do. I guess I could consider 2 to be the mother function here. How would you consider 2 to be the mother function of that numerator? Why would you consider it?
Because you could put e to the x in the denominator.
Nice. I like that. I like that thought. That e to the minus x is 1 over e to the x. I like that. And that's exactly the point is what I'm adding when I'm adding e to the minus x for x is bigger than 1. I'm adding a very, very small number. So 2 is, it's like 2 plus 0.00001. Who cares about that, right? So that's the kind of the thought process. And look, so we tried it. We cut off the 2 first. And then we saw that we had to do a lot of work. Doesn't sound like what we want to do. Right? We want to do nothing. At least I do all the time. All right. So good news is we're done for today.